Hi, my name is Colin Daniel, and I'll be talking to you about incorporating uncertainty into ecological forecasts using the SyncroSim modeling framework. So let's just start with a definition of ecological forecasting. This is defined by Clark et al. In their seminal 2001 paper. They said ecological forecasting is the process of predicting the state of ecosystems, ecosystem services, and natural capital with fully specified uncertainties. And these uncertainties can come in various forms, including uncertainty in our ability to estimate the parameters for a particular forecasting model, uncertainty due to the fundamental structure of our forecasting model, and finally, uncertainty regarding processes that are beyond the scope of our forecasting model. And returning again to one of the conclusions of the Clark paper, and that was that when reported at all, prediction uncertainties are typically confined to estimation error, which is often overwhelmed by other sources of uncertainty. And while this conclusion is now almost 20 years old, unfortunately, I believe it still applies for most forecasts of landscape change. So why are these uncertainties so often ignored? Well, I'd argue that stochastic spatial simulations, because they're so computationally demanding, they simply take too much time and effort to capture all the uncertainties. And because of this, most applied landscape modeling forecasts tend to ignore many of the uncertainties outlined on the previous slide. All this leads to the objective of the work I'm presenting today, which is to develop a general framework for projecting landscape dynamics that explicitly incorporates uncertainties in an effort to deliver more informed forecasts to decision makers. So our contribution to this goal has been the development of a software platform we call SyncroSim. And SyncroSim does a number of things to help landscape modelers deal with uncertainty. First, it provides built-in support for running space-time Monte Carlo simulations. It also provides extensive support for handling large spatial data sets. And these two features together help provide the foundation for tracking estimation error associated with landscape forecasts. SyncroSim also allows any number of models written in any language to be connected together in what we call pipelines, making it possible to explore uncertainties between and across models. And another key feature of SyncroSim is its built-in support for tracking all the inputs and outputs of your Monte Carlo simulations, making it easier to consider scenario uncertainty. So how does SyncroSim work? Well, you start with a model, again, written in any language, and then you make sure that all your inputs and outputs are stored in tables. You add a bit of wrapper code then to connect each of these input and output tables to SyncroSim. And finally, you create a matching XML file to go with your model code that describes the format of each of the inputs and outputs in your various tables. So with this basic wiring in place, SyncroSim then keeps track of all your inputs and outputs for you across all your models, all your scenarios, and all your Monte Carlo realizations. It also provides a built-in suite of tools that allow you to mix and match scenarios and to easily analyze the results. Finally, SyncroSim provides you with two alternative interfaces. First, a full command line API for programmers, which includes a package for fully controlling SyncroSim from R. And there's also an optional Windows-based user interface that helps deliver models in a format more suitable for decision makers. So let's now touch very briefly on one example of how we're using SyncroSim to help deal with uncertainty. And this is work that we've been doing with our colleagues at the US Geological Survey to try and forecast future stocks and fluxes of ecosystem carbon across coastal wetlands in the continental US, conterminous US. On the next few slides, I'll lead you through the workflow we've set up in SyncroSim for this particular project. And as shown here, we'll begin by loading a landscape simulation model into SyncroSim. In this case, we use a state transition simulation model, but it could be any landscape model. And then SyncroSim takes as input the initial map of land cover, along with transition probabilities between land cover classes, and projects stochastically, using a Monte Carlo simulation, the distribution of future land cover, such that there's one map for each Monte Carlo realization and each future time step in our simulation. So the first uncertainty we address in this modeling framework is the parameter uncertainty associated with our initial conditions. And to do this, we plan to use an accuracy assessment of the most recent land cover map to bootstrap a distribution for the initial cover class of each cell for each of our Monte Carlo realizations. Thus, we're sort of capturing the uncertainty in our initial conditions. We also are using the full historical time series to characterize the variability in the rates of change in land cover classes across our landscape. And we then sample from these empirical distributions to estimate the uncertainty or variability in the transition probabilities between states in our landscape change model. We're also considering scenario uncertainty in a more traditional way, which we've included by here in this example by looking at a range of alternative future sea level rise scenarios in our landscape change model. So now, given Monte Carlo simulation projections of land cover from our first model, we can feed those into a spatially explicit carbon budget model, which we then use to track fluxes of carbon between various carbon pools for each cell on our landscape. And by integrating this carbon budget model with the model of land cover change, we're able then to propagate the uncertainties from one model through to the other. We're also using field data gathered from multiple sites across our study area to estimate the variability in the initial pool sizes of carbon and also the flux rates for our carbon budget model. And finally, we plan to explore model uncertainty within our carbon budget model by comparing two alternative forms of carbon models. So to conclude, I still believe that forecasts of landscape change with fully specified uncertainties remains a challenge, and that we need to be paying more attention to the data management of our models in order to really move the bar forward on this front. I also believe that the SyncroSim platform that I've outlined here can help with this challenge. Finally, if you're interested in seeing more examples of SyncroSim in action, there are two other talks at this week's conference that provide a little bit more in-depth examples of how the framework's been used. And also, if you go to my iPoster, you'll see an example of how we're using SyncroSim to generate daily forecasts of COVID-19 infections and deaths for Canada. Thank you. Have a great day.